Fields. Fields. A field in physics is very much like you would expect it to be if you think of the natural meaning of the word field. You know, a field of roses in the meadow or something, you know. It's basically just a big area or a region of space. So here's what I'm going to define it as, and this is just kind of my own makeshift definition. I suppose there are many different definitions that you could use, but a field is a region of space, that is affected by or has an effect on a particular property. So we'll elaborate on that a little bit, see if we can't understand exactly what that means. It's a region of space that is affected by or has an effect on a particular property. So I'm going to give you an example of a field that's not physics. I want you to think about your mother making dinner tonight. So, you know, mom's cooking on the stove. Here's the stove. Let's draw a little stove here. There she is. And on the stove is a pot of, say, stew or something, whatever your favorite food is. And so what's happening, of course, is the stew is giving off an aroma. The smell of the stew is emanating from the stove. Now, you coming down the street, maybe you get off the bus stop as you walk towards the end of the driveway, and maybe the window's open a little bit. So here's the window open a little bit, and this smell wafts out the window down the driveway, and you begin to notice that something is going on. You smell a little bit of this stew. You're like, hey, mom's making stew. Yay, I love stew. Right? Actually, most people are not big fans of stew, right? Who loves stew?
I don't love it.
Yeah, it's okay. Depends what kind of stew. Anyway, your mom's making stew, so you smell it. But what happens, of course, is as you get closer to the house, maybe here's the house, you know, you get to here, and now you're sure. At first you're like, oh, is that stew? Is mom making stew? Not sure. It could be stew, or it could be those rotten leaves in the ditch, one or the other, right? But now you get to here, and you're sure now, oh, it's a stronger smell, so you know it's stew. And of course, even if you close your eyes, you can kind of follow the strength of the smell, and you can find your way into the kitchen and right over to the stove, and you'd be like, oh yeah, there it is, stew, right? Now you might think that, you know, out past the driveway, wait, let me go back here. Out past the driveway over here, you didn't smell anything. So you might think that the smell stops here. But what you didn't notice is there was a stray cat, 2 dogs, and a bear wandering around in the neighborhood out here because they smell the stew from, well, bears can smell stuff from miles away. They can actually take a bear from the garbage dump, tag it, put it in a helicopter, drop it off 200 miles in the bush, and by the next evening it'll be back in the dump because it can smell its way back. So, you know, this field of aroma, what I'm trying to say is it doesn't actually end. It just goes on forever. And the only thing that limits you is your ability to smell it. But it does get weaker and weaker and weaker as you go, the further away you get, right? Obviously. And in fact, if you're a bear, you can actually use the aroma field to smell your way towards something because the strength of the smell increases as you get closer to the pot on the stove. So you can just, if you start walking and wonder, if the bear is wandering around in the driveway and he starts to walk this way, he notices, oh, wait a minute, the smell's getting weaker, which makes him turn, and he follows his nose. That's the expression, right? Follow your nose. And as long as he keeps getting a stronger smell, he knows he's in the right direction, and he will eventually find his way right to the stove. So this region of space, all over here where the smells are, right? That's what we would call the aroma field. And I guess you could say, well, you know, what property is affected by this? Well, this is a hard one to find. I guess you could say the property of being hungry or hunger. Hungry things are affected by aroma field because they suddenly feel the desire to go and find out what's cooking, right? So that would be the property that it operates on. Okay? So the field can have an effect on hungry people, right? And draw them in. So let's compare that now to gravity. Let's think about what gravity does. So let's see if we can use the same idea to model a gravitational field. So for gravity, we have, let's draw ourselves a little Earth here. Earth, there we go. Continents there. There we go, little Earth. Maybe a little Africa over here. Greenland, whatever. There. So we have, we'll forget Australia, everybody forgets it. There's a little Earth. And Earth has a gravitational field. All around the Earth, the space around it. In fact, we talked about how in Einstein's theory of relativity, we picture that the space is warped or bent or somehow affected. So if you put Earth here, it affects the space around it, right? And of course, the property that we're talking about here, the property for gravitational fields is mass. Property is mass. If you don't have any mass, then you don't even notice gravitational fields. Most things have a mass, but a neutrino, for instance, is a tiny subatomic particle that we'll learn about later that has virtually no mass, and possibly none at all. It's hard to say. We don't really know for sure. But that means that a neutrino would shoot by the Earth, and it wouldn't feel anything. No pull. It wouldn't feel drawn into the center of the Earth. If I dropped a neutrino from my hands right now, it wouldn't fall. It would just do what it does, right? I guess if it wasn't moving, it would hover there. If a neutrino could be kept still and not moving. Most of the time they're moving at extremely high speeds. So they're not affected by gravity because you have to have mass to be affected by this field. Imagine a bear who cannot smell. A bear with no sense of smell, for whatever reason, right, is going to walk by your driveway and not be drawn into the stove at all. So no effect on anything that doesn't have mass. So what happens to things? Well, let's imagine that we put a little, let's take a ball. Okay? So we'll take a ball, and we place the little ball right here. A tiny little ball. Compared to the Earth, the mass of the ball is insignificant. All right? So we're going to call this a test mass. That's what it's going to be called, the test mass. Because we're using it to test the field around the Earth. And the definition for a test mass is it has to be tiny compared to the Earth. Because if it was big, like if it was Jupiter, well, it would make its own field. And Jupiter, being so massive, would make a field that overlaps Earth's field and messes everything up. So to find out what Earth's field is, we have to use something very tiny that's not going to mess it up too much, right? Right. Okay, so what would happen to this test mass if we dropped it here? Well, we all know it would be pulled in towards the Earth. It would feel, the effects of the field would be that it wants to go this way. And so we can draw an arrow to show that there's a force. This field, this is actually an example of a force field. You've heard of force fields in science fiction, right? You've got Luke Skywalker's in his little X-wing fighter, and they're shooting with laser beams, but he has shields all around his fighter. Those are force fields that absorb the energy somehow of the laser beams and protect him, right? Or you've seen how they can put a force field around someone and imprison them, and they can't get out. They can't walk through it. There are such things as force fields, not quite like in science fiction. We haven't learned to manipulate them to that effect yet, but maybe we will in the future. But gravity is a field, and it's a field of force, so it's a force field, right? So what would happen if you take this test mass and you put it way over here, the same little guy? Let's test over here on this side. Well, we would get an arrow that would be drawing towards the Earth. But I'm going to draw it a little smaller, because you're further away, and we know that the force of gravity gets smaller the further you get out, right? And so the field around the Earth, no matter where you put the test mass, put one here, let's put a bunch of them, little tiny balls all around, and what we would find, doesn't matter where they are, we would find that they would all feel a force inward. Some of them, the closer ones, would feel very strong forces, and the ones that are further away would feel small forces, but they would all be going in this way. So there's a definite direction associated with this field. Everything points into the center of the Earth. And there's a definite pattern in the strength of this field, right? Just like the aroma field, it's kind of the opposite. The aroma, well, no, it is exactly the same, isn't it? The aroma was stronger closer to the stove. And so here, the force is stronger closer to the earth. So what we can do is we can draw this in a slightly different way. We can just put the earth in the middle, and in fact, a dot works best because there's the center of mass of the earth. And we can draw arrows. If we drew a bunch of arrows close to the earth, we would see that, I'm going to draw long arrows here, because the force would be very strong in close, right? Strong force, all pointing in. But then, as you moved out, the arrows would get consecutively smaller, because the force is further away, but they're still all pointing in. And then out here, very small forces. So we could show the field like this. Oops, let's get rid of this guy for a minute. We could show the field with these little arrows. And of course, we've drawn some, but I could keep drawing them all around here, no matter where you go. That's enough, though, to give us an idea, right? Does this look kind of vaguely familiar to you? In grade 11, you did begin to study magnetic and electric fields a little bit. The other thing we can do is draw this, instead of worrying about the size of the arrows, we can simply draw the mass, and we can draw arrows in like this to show that this is what the gravitational field looks like sort of around the mass, and understand that it gets weaker as we go. So that means that if you take a little mass and you drop it anywhere in this area of space, in this field, it's going to follow the arrows. So if you drop it right there, whoops, let's go back. You drop it there, it's going to follow the arrow. It's going to feel it pulled in. And that's really all the concept is. It's fairly straightforward. Now, we can also model electricity like fields. We could take, instead of the Earth, let's consider an electric field. An electric field is a field, a region of space, but of course the property changes. The property that is being affected is not mass, but charge. A neutron has no charge. A neutron cannot detect an electric field. It has no effect. It's like the bear, can't smell. It just flies on by and says, I didn't see anything, I don't smell nothing, right? But if you have charge, like a proton or an electron, or some poor rabbit that's been rubbed by a piece of amber or something in a crazy experiment, you're going to feel the electric charge. In fact, if you were to charge yourself enough, it's hard to get this much charge on a human being, but if you were to charge yourself enough and you were to walk through an electric field, you would feel pulled in strange directions because of the field. But we don't notice that because we don't usually get all that charged. So an electric charge, well, let's take this example right here. Let's take a negatively charged object, and let's see what would happen. Well, we need to test it. The problem with charge, it's different than gravity. There's no such thing as negative mass, at least in our current understanding of the universe. Negative mass doesn't really play into these, what we call classical theories. There are ideas out there that there could be such things as negative energy and negative mass, but we haven't got a handle on them yet. So gravity, as far as we can tell, is always attractive. It never pushes you away, right? But because electricity comes in positive and negative, it can do both. It can repel and it can attract. So we have to decide, well, if I'm going to put a little test charge instead of a test mass, if I'm going to drop a test charge into the field, say right here, I have to decide what charge I'm going to use, a positive or a negative, because I'll get two different results. And so by convention, just to make sure everybody's on the same page, we all have agreed that we will define the field as if it was a positive test charge. So for electric fields, we always assume a positive test charge. Positive test charge. And we decide what we'll do. Well, a positive charge, of course, here would be attracted to the negative, right? And it would be pulled inward. And you can envision, if I put a little positive test charge anywhere, it would be pulled inward. And so this field would look very similar to the gravitational field that we drew over here on the other side. Here's the gravitational field around Earth that's based on mass, and if I keep drawing this, I could have a picture that looks almost identical, and this would be the electric field around an electron. Now they're not the same thing, because this one which is the electric field, only affects charge, or charged objects, and this one works on mass. Okay? So what we could say is that the mass here creates this field around it, and the charge here creates this field around it. So now it would be interesting to try to figure out if we can mathematically describe this field, right? So what we do is we're going to go back to our friend gravity, and that picture made sense at one point. We're going to go back to, if we get the smart board to cooperate, there we go. We're going to go back to our force of gravity, and we're going to look at the force of gravity equation that we already know about, thanks to Isaac Newton, m1 m2 over r squared. And of course what this does is if you have a mass right here, say Earth or whatever, and you put another mass somewhere else, then this tells us what the force of gravity is between these two objects, if we know how far apart they are, right? And the big G is the universal gravitational constant. So we've done that. But I want to show you what else we've done. What else we've done is we've identified that on the Earth there's a magic spot, right? A place where we live, where it's very convenient. So I'm going to draw my Earth a little bigger. Gravity works from the center of the Earth, but we all happen to live here on the surface. So the surface of the Earth, which is one radius away from the center, is a spot that we conveniently use all the time. And so what we've done is we've taken this formula right here, and we've used these three numbers. Remember this. We put in the G, we put the mass of Earth right here, and the other mass would be the mass of the tiny object. And then we put the radius of the Earth, which is where you'd be if you were on the surface. And guess what we got? We got that little magic number, 9.8. And we gave it a name. We called it little g. Well, little g, his official title, is the gravitational field. I guess you could say the gravitational field. You could say he's a constant, sort of, at the surface of the Earth. But I'm just going to say he's the gravitational field value at Earth's surface. Now we use this a lot, 9.8, because we live here, but we could find a gravitational field value anywhere. It doesn't have to be at the surface. I could find a spot way out here and use a different R, use this R, right? Same mass, same Earth, but use a different R. I'd get a different number. We've seen that. I might get 7.2 or something, or 6.9, because as further you go, the less it is. That's why you can't use G too far away from the surface. So I could find the value of Earth's gravitational field anywhere around the Earth. I could find it here, or here, or here, or here. All I need is different R's. And so this little expression that we have here tells us mathematically how to determine the value of Earth's gravitational field. If Fg equals g, mass of Earth, times the mass of, say, a test mass, I'll put a little t. And instead of Earth, I'm just going to put any object. Because what if it's not Earth? What if it's something else? So let's put O for object. And then over here, R squared. Well, it turns out that these three numbers, right, will produce the value of Earth's gravitational field at any point. And so I can call that G. Now, it's the mass of the object. The little MO, I'll explain in a second, represents the mass of the object who's making the field. Earth's gravitational field is made by Earth, right? So this little m, it's not the mass of the test mass. That's so small it doesn't matter. This is simply the mass of the object that is creating this field of space. So it's the mass of Earth that goes here, and it doesn't matter what other mass you put there. We need to give it a name, but we can't call it little g anymore because that's only at the surface of the Earth. We need to give it a sort of a general name. Well, if we call it g, we could call it g, I suppose, but we'd have to understand that this little g could move and change and not be 9.8. We don't really give it a special name in gravity because everything we do in gravity, we use little g because it's on the surface. Like Who's floating around in orbit? There's only 6 people in space right now. And, out of the 7 billion, it's not that big a deal. So we don't conveniently give this anything of a name except for at the surface, where we call it G. But we can use this idea as a model. Let's go down now and let's compare. What do we know about electricity? Well, the electric force is equal to K Q1 Q2 over R squared. It looks almost identical to gravity, doesn't it? And so the electric field, if we do the exact same little thing, what if we take these 3 numbers, right? What we will get is K, Q of the object that's making the field, the big object in the middle, or the charged object in the middle, divided by how far the test charge is from it, and we'll call that the field strength for electricity. Same thing. But we need a name, or we need a symbol for it. Well, electricity starts with E, so why don't we call it E? I like to use a scripted E like this, because we also use an E for energy, remember? Now some textbooks use a Q for energy, and they use other letters, so it all depends, and as long as we know what we're talking about. They use a capital E like this sometimes, but I don't like that one because we use that for energy. So it's confusing. So I use this little weird-looking E. And this little weird-looking E, sort of an italic E, I guess you could call it, represents the electric field strength. Okay? Now, if I just figure out the numbers using this equation, I get the magnitude of the electric field strength. But electric fields are vectors. They have directions. We have to infer the direction by looking at the laws of electric charges and so on, right? So if you're surrounded by if you're a negative charge making the field, the arrows were pointing in, we have to kind of remember that there is a direction. These are vectors, electric fields. So we have to always consider the direction. With gravity, the direction is pretty easy. It's always in towards the object. But with electricity, you can also have repelling and away from. So we'll talk about those in just a second. So this is a very important equation. It allows us to calculate the electric field strength. Now, here's the catch. We had a nice little number for gravity, 9.8. There is no number for electricity, because if you're a charged object, well, there's no surface. There's not people living on the surface of a tiny pith ball somewhere. Maybe there is, I don't know, but if they are, they're not bothering us and we don't care much about them, right? So there's no magic spot. There's no surface or place where we could say, this is a convenient spot, let's put in numbers and get a number. This number is always going to be variable. So when you're dealing with electricity, there's no shortcut. There's no let's just use little g like gravity. That's the only difference, but it is the same idea. So in other words, you could be anywhere around a charge, so you're always going to have to calculate the field strength, and there's no special spot that we give any significance to. All right, so let's just draw a couple of pictures then. So we have gravity. Here's a mass. And the gravitational field looks like this. We've already done that. We say that looks very much like the gravitational field around a negative charge. Here's a negative charge. I said gravitational field. I meant electric field around a negative charge. Well, let's think about a positive charge. Drop a positive test charge all around here, it's going to be repelled in all directions, isn't it? And so we see this. This is what the field would look like around a positive charge. And this is the part that does not exist for gravity as far as we can tell. There's no pushing in gravity. But the magnitude of this would still be the same, right? You would still calculate for both of these, K, the mass of, or the charge of the object, divided by R squared. This would give you the magnitude, but you have to know the direction based on what kind of charge there was in the center. But that's pretty simple because we know opposites attract and we know that similar charges repel, and you're always using a positive test charge to determine which way you would go. So it's like dropping a positive charge in there, and which way would it go, basically. Now, the unit for this, if you look at this formula that I just drew, if I multiply it by the other charge, the charge of the test charge, then I get back to force again. That would end up giving me the force equation right back again, wouldn't it? So this part right here is measured in newtons divided by charge, right? So newtons per coulomb. So electric field strength is in newtons per coulomb. Newtons per coulomb. And what it means is, if you drop a coulomb of charge anywhere in the field, let's say you drop a coulomb, 1 coulomb of charge here, and the field strength is 8,000, it means there's 8,000 newtons of force pushing on every coulomb that you drop there, right? 8,000 newtons of force are pushing on every coulomb. So if you drop 7 coulombs, 56,000 newtons of force. So it's like a sort of a price per pound when you go to the grocery store and you buy, I don't know, slices of ham for your lunch, right? They tell you how much per pound, and then it just matters how much you're going to buy. So the field strength is kind of like that. Newtons per coulomb. When you do the gravitational field strength, what it is it's not newtons per coulomb, it's newtons per kilogram, right? And you get both, newtons per kilogram or newtons per coulomb, and if you had a different force field on a different force, it would be slightly different. Okay? So, let me just show you one more thing before we finish. Let's go back to our cutesy little shortcut for gravity. Fg equals g, m1, m2 over r squared. And if we take all of this and we replace it with g, we were able to get Fg equals mg, where this time, this is the mass of the test object, the test mass. And this is the gravitational field strength near the Earth's surface. It's 9.8, but we could calculate it anywhere. We could still use this equation if we were going to get the right g, right? We could still calculate this number and get wherever you were. Let's say you're out in orbit. We can calculate that and get 6.4, and then we could do 6.4 times the mass, and that would still work. We just don't do that very often. With electricity, right, Fe, the electric force, is K, Q1, Q2 over R squared. We could do the same thing. We could turn this into the little E, or the weird-looking E, because it's electric field strength, and we could then multiply that by the test charge, Qt. So Fg equals mg is exactly the same sort of the kind of equation as this one, which is a way of determining the force using the test charge and the electric field strength. So there's 2 equations we can use, right? So I'm going to summarize it all sort of right now in the chart. There are 2 points of view. So the first point of view, POV, POV. The point of view of the object making the field. If you have a giant mass and you want to know what the field strengths are around that field, well, you would simply do, for gravity, we've got G equals big G, mass of that object, and then the distance away. For electricity, we've got E equals K times the charge of that very same object over the distance squared. But you could also look at it from the point of view of the test object. The test object. And that would mean that the force of gravity is equal to the mass, the test mass, times g. That's just our equation, mg. And for electricity, the force, the electric force is Q test times the electric field strength. 9 times out of 10 with gravity, we use this one because we're near the surface of the Earth. But with electricity, we use both of these sort of together. There's not one that's any better than the other because both points of view are equally valid, right? This one is the point of view right here from the Earth's surface where we live, so we use it more often. But with electricity, we have to get accustomed to having both in our back pockets. So if the information you're given has a lot of information about the object making the field, you can do this and figure out your E. But if it has more information about the test charge that you're dropping in, you can do this, and you can get your FE this way, right? Of course, you have to know the field strength in order to do that. Often with electricity, there are 2 questions in one. You'll get a question, and you'll have to first figure out the field strength because there's no magic 9.8 number. So you can't just pick a number. You have to first figure it out, and then you would use it over here, and then you could figure out the force. So with electricity, we often use these two hand in hand, whereas with gravity, we have the shortcut that we use. And that's really the basic difference between them. And so that's fields and field strength. So if you want to do a couple of quick examples just to see how it would work out, let's do them. So here's example 1. Calculate the field strength. Let's do electric field, since that's what we're really after. I was using gravity just as a model. Calculate the electric field strength 0.2 meters from a 6 microcoulomb charge. And it'll be positive, of course. Positive charge. Let's put a plus just to be safe. All right? So we're talking about a microcoulomb. The 6 microcoulomb charge is here. I'll put 6 in there. Here's the charge, 6 microcoulombs. And it's what's making the field. So obviously in this question, I'm looking at the point of view of the object that's creating the field. So the other, what I want to know is if there's a magic spot that's 0.2 meters away, let's put it here, 0.2 meters. I'll put a little distance in there. And we don't worry about the radius of the charge. We always consider charges to be point charges, right? So although in the picture it looks like there's extra space here, we don't worry about that. Not only with large objects like planets for gravity and such. So with electricity, it's not a big issue. So it's 0.2. So what do? Well, the electric field strength is Q over R squared. And it's the Q of this, QO. Some textbooks, I should point out, they give this a name. They call it the master charge. The object, the charge that's making the field is sometimes referred to as the master charge. So you might see a little M there. In your textbook, I think they do that. But it just means the object in the middle that's making the field. Okay? So if you see QM in your textbook, that's what they mean, master charge, as opposed to the test charge. We don't even have to know anything about the test charge. We're just going to pick that magic spot and see what we get. So 9 times 10 to the 9 for the K. And of course, the charge is 6 microcoulombs, so 6 times 10 to the negative 6 coulombs, and 0.2 squared. And then we crunch out the numbers to see what we get. Let's see. So 9 times 10 to the 9 times 6 times 10 to the negative 6 equals divided by 0.2 squared. And it's a big number, huge number. The answer I got, let's see if you get the same one, was 1.35 times 10 to the 6. So 1,350,000 newtons per coulomb. That means if you drop a coulomb of charge right there, that far away from this tiny little object, it'll feel a force of 1.35 times 10 to the 6 newtons. Huge force. But remember, the reason it's so big is because a coulomb of charge is gigantic. Most of the charges you would experience in real life are like microcoulombs. So if you drop a microcoulomb there, it's only 1.35 newtons, right? Very small force. So when you were doing your pithball experiments in grade 9 with the ebonite rods and rubbing them with fur and watching the balls bounce around, you were dealing with forces around 1.35 or so, rather than big giant forces like this. But every coulomb of charge you drop in this spot will feel that force. If you drop 20 coulombs in there, it'll be 20 times that, right? So the second part of this question could be, what force would be experienced? Let's call it a part B question. What force would a 7 microcoulomb test charge feel? It's not technically a test charge. I called it a test charge just to make sure you know which perspective we're talking about. It's very close in charge to the original one. So what would it feel? What force would it? Well, then you can do Fe equals Q times the electric field strength. So you could do 7 microcoulombs, 7 times 10 to the negative 6, times the strength of the field you just figured out, which is 1.35 times 10 to the 6. And if you do that, you'll see that it's Not a very big force at all. So 7 times 10 to the negative 6 multiplied by 1.35 times 10 to the negative 6. What, 9 times 10 to the negative 12? Is that what you got? Double check for me. No, that doesn't make sense. 7 times 10 to the negative 6 multiplied by 1.35 times 10 to the 6. 9.45 newtons. So not much, not a very strong force. Right? Now also, notice what we did. All we really did is take the field strength. Okay, I'm just going to show you this one more time. All we really did in those two questions is take the field strength E, which is K, Q over R squared, and multiply it by a Q, right here. See? Right there. Which is really the same as doing this. F equals K, Q1, Q2 over R squared. So we haven't really done anything different. We're just looking at it from a totally different perspective. We're looking at it from this point of view of the field strength, but we're effectively doing the same thing. That is the same as that. So we're kind of breaking it up in two steps. You might ask why? Well, because sometimes this is a better way to look at it, that's all. So this whole lesson is just a matter of perspective rather than something actually new. Same concept, but not anything new. And I think we'll stop there, and we'll look at some examples in the next few videos. We'll do some example questions.